In this video, we continue our discussion of amines by going over ways to synthesize amines via reduction reactions, where we can reduce any of the following circled types of molecules to amines by using either hydrogen and a metal catalyst as our reducing agent, or lithium aluminum hydride followed by the use of acid. Those are two of the common reducing agents that we have learned in the past, and those will both be applicable here. So to remind you about what these functional groups look like, the azide group, which we can reduce, is a group where we have R, which will be our alkyl group, directly bonded to 3 nitrogen atoms, and the most stable resonance structure for this N3 group that makes up the azide functional group looks like so. We'll have a positive charge on the nitrogen in the middle there, negative charge on this nitrogen, and then this one will have no formal charge, but it would have a lone pair of electrons there if we were drawing out the complete Lewis structure. So by starting with an azide and treating it with a reducing agent, we would yield an amine as the final product, where these 2 nitrogen atoms would be eliminated from the molecule. We'd be left with this nitrogen as a primary amine group by bringing in hydrogens donated by the H2 or by the lithium aluminum hydride. Likewise, we can also carry out reduction reactions of nitrile groups. And as a reminder, the nitrile group is our alkyl group bonded to a carbon which bears a triple bond to a nitrogen atom. That is also referred to as a cyano group, as well as a synonym for that. So you may see me alternatively refer to this nitrile group as a cyano group throughout. Nitro groups are another group that we can reduce to form amine products, and we have a nitro group referring to an R group that's directly bonded to NO2. So in each of these cases so far and throughout, what we're going to be doing is we are going to be reducing by lowering the number of carbon-nitrogen bonds in the case of the nitrile and replacing with hydrogen atoms to fill in the octet on the carbon and the nitrogen, giving a primary amine group here. Similarly with the nitro group, we're going to be reducing the molecule by eliminating these oxygen atoms and replacing them with hydrogens to give an amine group there as well. Analogously, when we come to the amide, remembering that an amide group is where we have our R group, which would be our alkyl group, a carbonyl, and then that's directly bonded to a nitrogen, which is connected to 2 R groups, and those R groups can be either carbons or hydrogens. What's going to happen here in this reaction is that the reduction will ultimately remove the carbonyl group, replacing it with hydrogen atoms, so that we ultimately have, in place of this carbonyl, a CH2 group, and therefore we would end up with an amine functional group. And then finally, we can also reduce the imine groups, which we talked about in the last chapter about how to synthesize those. We can reduce an imine group to an amine group, and remember that the imine had the following structure. And these R groups could all be the same, or they might be 3 different R groups here as well, and they can be carbons or hydrogens. So our imine, by treating with a reducing agent, we would be adding hydrogens across this carbon-nitrogen double bond in order to reduce to an amine group, AMINE in that case. So we're going to take a closer look at each of these reactions as we go through this video, looking at examples of using specific reactants to create amine products. We are not going to go through any mechanisms in this video because some of these mechanisms, particularly reactions with lithium aluminum hydride, we went through in earlier chapters with other types of molecules, and there's simply not enough time to go through the mechanisms for every single one of these types of scenarios. So in each case, we need to be aware that we can use common reducing agents to reduce each of these functional groups to amines. Now, one question that may be simmering in your mind is we've talked previously about 3 main reducing agents: hydrogen with metal, lithium aluminum hydride with acid, and then the third type of reducing agent that we talked about was we talked about using sodium borohydride. In this particular case, sodium borohydride will not work. It is not a strong enough reducing agent to enable the reduction of any of these types of functional groups to yield amine products. And so as you're going through these and designing syntheses, be aware that you will not be able to use sodium borohydride as your reducing agent. If the goal is to create an amine product, you will have to use either hydrogen with metal catalyst or lithium aluminum hydride with acid in each of these cases. That's the theme that is going to tie all of these reactions together, is the type of reducing agent required to create the amine product through these reduction reactions. So in this example problem, we are going to provide the major organic product that would result from the reaction that's shown here going vertical on your page, as well as using the same starting material in a different reaction using hydrogen with a metal catalyst. Now, before we get into this specific problem, I want to remind you of some general rules for the use of different reducing agents. Specifically, since in this video, the reducing agents we're focusing on are hydrogen with a metal catalyst and lithium aluminum hydride, followed by acid, we want to be sure that we're all on the same page here about what these will and will not reduce. So I'm going to go ahead and fill in that hydrogen and a metal catalyst will reduce carbon-carbon double bonds of alkenes, carbon-carbon triple bonds of alkynes, carbon-oxygen double bonds of aldehydes and ketones, and then generally, this reducing agent is not strong enough to reduce carbonyl groups of carboxylic acids, which I'll abbreviate as Ca, and esters, because those are too heavily oxidized since they have a total of 3 covalent bonds between the carbons and oxygens there due to the carbonyl group and then the additional single bond to an oxygen. So those cannot be reduced by H2 and our metal catalyst. And these rules are in addition to what we looked at on just the last slide where we saw that both of these will reduce all of those different nitrogen-containing groups to amines. So going on down the list then, for lithium aluminum hydride, to compare and contrast it with what will be reduced by hydrogen, lithium aluminum hydride will reduce the carbonyl groups of all sorts of molecules, carboxylic acids, esters, aldehydes, ketones, and pretty much anything else you could find along the way that would have a carbonyl group. It's a very strong reducing agent for carbonyl groups. However, lithium aluminum hydride will not reduce carbon-carbon bonds. So it will not reduce alkenes, and it will not reduce alkynes. So we have to keep these guidelines in mind as we carry out these reduction reactions with our two reducing agents that we recognize will both reduce nitrogen-containing groups to amines. So in our example here, as we start with our azide starting material and we treat it with hydrogen with a metal catalyst, we see down below in our rules and guidelines that hydrogen and a metal catalyst will reduce carbon-carbon double bonds. And so yes, we are going to reduce this alkene group here as well as the nitrogen. It's not possible to do the reduction reaction selectively and reduce just one or the other group. Instead, it's going to be an all or nothing thing generally. It's going to reduce both of those. And so hence, the product of this reaction will correspond to converting that alkene into an alkane, hence reducing the alkene to an alkane since the reduction corresponds to bringing in additional hydrogen atoms. And also that azide group, N3, will be reduced to an NH2 group. And the other two nitrogen atoms from the azide would go away as essentially leaving groups during the course of the reaction. They are not going to be part of the major organic product. On the other hand, if instead of treating our starting material with our hydrogen and metal catalyst, instead we treat it with lithium aluminum hydride, what's going to happen is the lithium aluminum hydride will not reduce the carbon-carbon double bond. Carbon-carbon double bonds are impenetrable to lithium aluminum hydride or sodium borohydride for that matter. And so as a result, this reaction will selectively reduce just the azide group. And so therefore, in our product, we are going to leave the carbon-carbon double bond in place, and we are going to instead just reduce the azide group in 3 to NH2. Now let's continue this with another example problem. I'm going to leave the rules down below on the screen here so that we can continue to refer to those as we do these additional example problems. So now we continue with this example where we mix things up a bit because rather than asking for the product of the reaction, instead we ask what is the reactant or reactants that will allow us to convert our nitrile starting material to our final primary amine product. So in this particular reaction, we have on our smorgasbord 2 possible ways to go about reducing nitrogen-containing groups to amines. That was, we could either use hydrogen with a metal catalyst, or we could use lithium aluminum hydride with acid as the second component of this. So in this particular reaction, we could definitely use lithium aluminum hydride as our reducing agent. So we could write a number 1, lithium aluminum hydride. Keep in mind that it is essential that you use that number 1 there to indicate that the lithium aluminum hydride is added first, and then after that has happened, you add your source of acid. You could also include here, if asked to provide the solvent, THF, tetrahydrofuran. That is just the solvent, and that reaction is not playing a direct role, so there's a variety of options there possible for solvent. What's doing the work of the reaction is the lithium aluminum hydride. It's acting as a hydride donor to donate hydrogen atoms in that form of hydride to both the nitrogen atom here and the carbon atom here, essentially adding across that carbon-carbon triple bond multiple times in order to convert the triple bond to the single bond that we see here, and adding hydrogens on the nitrogen and hydrogens to this carbon, so that triple bond is no longer present at the end. Instead, these hydrogen atoms from hydride have been donated. So that's one possible route to go about things. What about the other thing on our smorgasbord here? That was hydrogen with a metal catalyst, such as platinum. Doesn't have to be platinum, but hydrogen with a metal catalyst. So in our guidelines here, in our rules, we listed that the hydrogen metal catalyst reduces alkenes, alkynes, and carbonyl groups of aldehydes and ketones. So you might have some pause as you think about this and you look at, okay, it'll reduce alkene groups, so what about the aromatic ring double bonds? Would we destroy those by treating the reaction mixture with hydrogen and a metal catalyst? And the answer is no. Due to the fact that our aromatic rings are so inherently stable, that makes them extremely non-reactive. The main type of reaction that those groups will undergo is the electrophilic aromatic substitution, where you substitute out one of the hydrogens on the ring for some electrophilic group rather than destroying the aromaticity. So when we say that we will reduce the carbon-carbon double bonds of alkenes, we literally mean just alkenes. These reagents won't reduce aromatic rings due to the fact that the aromatic ring is so stable, and by stable we mean it's extremely non-reactive. It's very low energy to start with. The activation energy required to destroy that aromaticity is extremely high, and it's not going to be favorable for that aromaticity to be disrupted by doing an addition reaction. So we will not be able to reduce aromatic groups using hydrogen and a metal catalyst, and hence that opens up a second option for this reaction, which is that we could use hydrogen H2 with a metal catalyst. Now, to continue to highlight these reduction reactions, we'll do another example. In this reaction, we will take this molecule and react it with lithium aluminum hydride followed by dilute acid, recognizing that lithium aluminum hydride is a reducing agent that selectively reduces nitro groups and all types of carbonyl groups, but not alkene or alkyne groups, we acknowledge that to get this problem right, we need to leave the triple bond in place and reduce the NO2 group by replacing the oxygen atoms there with hydrogen. So it becomes NH2. Those hydrogen atoms are donated from our lithium aluminum hydride and our acid, giving us an amine in the final product. Continuing this theme, we can look at reducing amide functional groups. In the amide functional group, we will go ahead and do an example where we will start with our amide, like so. And I'm going to reduce, in this particular example, I will reduce with H2 and our metal catalyst. The result of this reaction with H2 and metal catalyst, or the result of reacting with lithium aluminum hydride and dilute acid, is the same, and that is the carbonyl group becomes reduced ultimately all the way down to a CH2 group, and the nitrogen then is hence part of a primary amine group. And so we just redraw all of the molecule, except that we will replace the carbonyl group with instead a CH2 group, like so. So confirming that I haven't added or deleted any carbons from the chain, we have 1, 2, 3 carbons in our chain, 1, 2, 3 carbons here, followed by the nitrogen, and the nitrogen has 2 alkyl groups directly bonded to it. And one thing that's noteworthy about the reduction of the amide groups relative to the other groups that we've learned so far is that you'll notice here that we have created a tertiary amine, versus the other reactions we looked at so far are all created primary amines. So this provides us with a way to create secondary and tertiary amine groups within molecules. Reduction of the nitro groups and the nitrile groups and the azide groups only allowed us to create primary amines. So let's continue and look at one more additional example. I'm going to erase our top example here so that we have space to go ahead and continue working here. So I'm just going to get rid of that top example. And I'm going to replace it with an imine as our last type of group that we will show we can reduce in these reactions. So we have a carbon-nitrogen double bond as the hallmark of an amine functional group. And I'm going to go ahead and place on this amine group a CH3, like so. And I will reduce this. We could reduce this using either lithium aluminum hydride or H2 and the metal catalyst. Just to keep things mixed up here, I'm going to use the lithium aluminum hydride, LiAlH4. THF is our ether solvent, and then adding dilute acid to adjust the pH just enough to provide the proton necessary for finalizing the reaction. So what's going to happen here is that hydrogens are going to be added across the carbon-nitrogen double bond here, so that the pi bond goes away and we have a complete octet of hydrogen atoms here and here on the carbon and the nitrogen. So let's go ahead and draw that out. So drawing out my carbon chain the same length as before, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Got the carbon-nitrogen bond in place. We'll put the CN bond in. The carbon-nitrogen bond here to the methyl group stays in place as well. And we plug on a hydrogen atom here onto the nitrogen, so the nitrogen has its complete octet, keeping in mind that there would be a lone pair there on the nitrogen, there as well as here on the reactant side. But it's not necessary to draw that in a line angle form. I'm just showing it for emphasis there. There would also be a hydrogen would have added here as well, so that this carbon maintains its complete octet in our product. And keep in mind, this reaction has also, as we've demonstrated, yielded a secondary amine product out of this reaction. And so this is going to be a way to create secondary amines. And so these are our two approaches that I've left here on the screen that will allow us to create secondary or tertiary amines. In the case of reducing an amide, that is the only route we have learned so far that we can use to create a tertiary amine. This reduction of an amine could synthesize anywhere from a primary amine all the way up to a tertiary amine, depending on the structure of the amide group. And then with our imine reaction, that can create up to secondary amines. So in other words, it can create primary amines or secondary amines depending upon what's bonded to the nitrogen atoms. In this case, the nitrogen had an alkyl group bonded to it, and so therefore the reduction of that CN bond creates a secondary amine. So these are going to be two useful ways, reduction of imines and reduction of amides, to create amine products that go beyond just primary amines. So we've discussed different types of functional groups that we can reduce down to amine groups. Now, one thing that may be in your mind as you are thinking about this is we haven't recently talked about how you can actually create azide or cyano groups. So if you were aiming to reduce an azide or cyano group, you would first need to create that within your molecule. So how do we do that? Well, this is a throwback reaction to our nucleophilic substitution reactions. Specifically, the SN2 reaction with an alkyl halide was a common way to go about introducing azide groups and cyano groups into molecules. So let's just do a quick reminder of that nucleophilic substitution, specifically SN2, the type of mechanism where the nucleophile comes in and attacks at the same time the leaving group leaves. And we could carry that out here. We'll show starting with a non-sterically hindered alkyl halide, such as this primary alkyl halide shown here. This reaction sometimes is effective with secondary alkyl halides as well. The trick being that the alkyl halide has to be relatively non-sterically hindered. So if you have two small alkyl groups bonded to your alkyl halide, that could potentially work in an SN2, but if it gets too sterically hindered, then the steric hindrance is going to be too great for the reaction to occur very effectively. So with a non-sterically hindered alkyl halide, such as a primary alkyl halide, and in some cases a secondary, what we can do is react with sodium cyanide, NaCN, and what that provides to the reaction is that is going to provide a source of the cyanoanion, where the carbon behaves as a carb anion because the bond between the carbon and sodium is very heavily polarized, with carbon taking the lion's share of the electron density from that bond, since carbon is the more electronegative atom by far. So the carbon behaves as a carb anion, and so what it's going to do in this reaction is it will come in acting as a nucleophile, an anionic nucleophile to be specific. It comes in, attacks here at the electrophilic carbon as the leaving group leaves, giving way to our nitrile product. And the nitrile product will have a carbon chain that is extended by one carbon relative to the starting material. So our starting material here had a total of 1, 2, 3, 4 carbons. Our final product has 1, 2, 3, 4, 5 carbons because we introduced that new nitrile carbon atom right here. So this is a way to make a new carbon-carbon bond as well, which is a really valuable thing to be able to do. Likewise, if in your synthesis, rather than adding a carbon to the chain during this process of nucleophilic substitution, you wanted to bring in just the nitrogen atom that is necessary for reducing to the amine group, you could use sodium azide, NaN3, and that provides a source of nucleophilic nitrogen anion. And so what would happen here in this reaction mechanism is that the N3 anion would come in via its lone pair of electrons, form a covalent bond via the electron pushing arrow we have here as the leaving group leaves, to create in the final product a 4-carbon chain with our azide group N3 at the end of that 4-carbon chain. And then from there, each of these would be suitable for reduction to our amine product. So you could take either of these two compounds, treat it with our reducing agent, and yield an amine product. So this is a multi-step route that will enable the creation of amines from alkyl halide starting materials, where we create first a cyano group within the molecule or an azide group and then reduce to the amine as the final product using these SN2 type reactions prior to the reduction.